We continue with Chapter 8, and today we will look at subtopic 8.2 Poisson distribution. Let us look at properties of the Poisson distribution. Number 1. It describes discrete or individual occurrence over an interval. The occurrence in each interval can range from 0 to infinity, means there is no limit to it. Number 3, each occurrence is independent of one another and not related to each other. Number 4, the expected number of occurrences must hold constant throughout the experiment. Now, the most common tips or hint for us to identify whether it is Poisson or not. Normally, we look at either the occurrence is given over an interval or not. And we'll check whether the occurrence range from 0 to infinity. Remember, for binomial distribution, normally number of trials is given and it's given obvious. Let us look at some examples so that we can better understand the property of Poisson distribution. The number of cars visiting a service station in a day, the number of floors in a given length of material, the number of telephone calls arriving at a company's switchboard in a given minute, the number of cases of rare blood disease per 10,000 people, and number of bacteria per liter of water. Let us check how can we identify interval here. The first one is cars visiting a service station in a day. That's the interval. The second one, number of floors in a given length of material. That's our interval, a given length. It could either be in meter, it could either be 2 meters. The third one, the number of telephone calls arriving at a company switchboard in a given minute. It could be in 5 minutes. Number of cases of rare blood disease per 10,000 people. So that is our interval. And a number of bacteria per liter of water. Interval is per liter. It could be given in every 2 liters or so. Poisson distribution can be expressed in this. This means X is a Poisson distribution with lambda is the mean or the average or the expected value. The formula to calculate the probability of a Poisson distribution is given by this formula. Probability of any given number of occurrence is given by exponential e to the power of negative lambda multiplied with lambda to the power of x over x factorial. For x, 1, 2, 3 onwards until infinity. For those of you who don't know how to find x by x factorial, just look for this button, shift and press it. Let us look at example 5 now. The question for example 5 is this. If X is a Poisson distribution with lambda, or also known as mean or average, is 1.3, find probability of X equals to 3 and probability of X greater and equals to 1. From this expression, we can see clearly that lambda is 1.3. So to answer A, probability of X equals to 3, the formula is this. We just need to plug in the value. And that is our answer. B. Probability of x greater and equals to 1. We can list down that when x greater and equals to 1, we are asked to find the probability of x equals to 1 plus probability of x equals to 2 until, since it is a Poisson distribution, it is until infinity, which is impossible to do. So instead of doing so, we just write it as 1 minus whatever not included in here. So what's not included in there is probability of x equals to 0. Plug in the values into the formula, and that is our answer. Example 6. Question for example 6. The average number of cars passing a speed camera in an hour which are exceeding the speed limit is 6. What is the probability that 7 cars passing the camera will be speeding in the next 2 hours? At least 2 cars will be speeding in the next 1.5 hours. We are given average here. The average for an hour is 6. So this is actually the lambda for 1 hour. If you look at question A, 7 cars passing the camera will be speeding in the next 2 hours. So we have to find the lambda accordingly. We are given the lambda for 1 hour, but the question is asking for 2 hours. So we have to change our lambda accordingly. Same goes to B. The interval is 1.5, so we need to change the lambda accordingly. Question A is asking us to find the probability that 7 cars passing the camera will be speeding in the next 2 hours. So let x be number of speeding cars in 2 hours. Lambda, we remember that we are given lambda for 1 hour is 6. So the new lambda for 2 hours is 12. And we can express x as a Poisson distribution with lambda 12. This is the formula. Substitute the values into the formula, and this is our answer. Question B is asking for the probability that at least 2 cars will be speeding in the next 1.5 hours. So this time we will let y, since we have already used x in the previous question, let y be the number of speeding cars in 1.5 hours. So again, we need to change the new lambda, the lambda for 1.5 hours. So lambda is equals to 9. So now we can express that y is a Poisson distribution with lambda 9. The question is asking for at least 2 cars. At least mean minimum is 2. It can be more. Can be more. So if we list down, we can see that we are asked to find the probability of y equals to 2 until forever. But instead of doing so, it will be easier to find y minus whatever probability which is not listed above here, which in this case, probability of y equals to 0 and probability y equals to 1. This is our formula after we substitute the value in. To make our calculation easier, we can factor out e to the power of -9. And this is our final answer. That's it for today. Thank you. and have a nice day, everyone. Bye.